So I'll start, okay, to derive the Bernoulli, I'll start with this type of system. Okay, so here we have a pipe, okay, with different diameters. If you notice at the inlet, this pipe is having the diameter of D1. Okay, that's why the surface area is A1, but it undergoes a reduction of the pipe. The pipe becomes smaller at other point. That's why we have A2 here. Okay, this basically the system that we are going to use to derive the Bernoulli equation. So before we proceed, it is important for us to write the assumption, okay, the assumption that we are going to use. If just in case you are not working with this assumption, okay, for example, you don't work with incompressible fluid, because this will be the first main important assumption. Okay, we need to ensure the fluid is incompressible. So meaning that you cannot use the Bernoulli equation to calculate the pressure difference or head or velocity or any other properties that you are asked. You need to find out different approach to solve your problem. Okay, so the first important assumption must be incompressible fluid. Okay, okay, this is very important. This will lead us to the second assumption, okay, because incompressible fluid, meaning that the density of the fluid is constant. Okay, so at any position on this system, let's say maybe the fluid is here, and you compare the density of the fluid here. If you could take any density measurement, perhaps you take the sample of the liquid, you measure by using densimeter or hydrometer, for example, then you would notice that there is no change in their density. Okay, so that's why we say the density is constant at anywhere in this system. And we have the third assumption here in order for us to use the Bernoulli equation. So we expect that there will be no viscous force. Okay, what does it mean? It means that energy will be fully conserved. Okay, so at any point in this piping system, the energy of any part of the fluid will always be conserved. Okay, that's why we can proceed once we fulfill these three assumptions to do the Bernoulli equation. Okay, so we have earlier, we need to combine the energy equation. Okay, the energy equation, the conservation of the energy based on those assumptions basically can be combined, okay, as the net, okay, the net work that apply to the fluid. Okay, we have dW. D refers to differential. W is the work. Remember, work is also energy. Okay, and then it will be equal to dk plus du. Okay, K here is kinetic energy. Kinetic energy. While U here, I simply use term U just to show about potential energy. Okay, potential energy, some people like to use PE, or some people also write it as U. So in this case, I just use one letter. Okay, so dk and du. So this is the conservation energy that we are going to have for this type of the system, because we ensure that energy at any part of the fluid basically will be conserved. So we are going to analyze this energy term one by one. Okay, dW, or the work that apply to the fluid, and then the change in kinetic energy, as well as the change in potential energy. So let us first talk about the first term. Okay, work. Work that was done or is done on the fluid. Okay, work, if you still remember from thermo, is energy, right? And what is the definition of work? Okay, in physics, in elementary physics, if you still remember, or maybe someone remember, anyone remember how you define work? Any equation that you remember? What is work? It's very, I mean, we use it a lot actually during our senior high school physics. Maybe some of you still remember. Okay, Wei Kyung, P multiplied by dV. Okay, yes, that's you are still fresh. You still remember a lot about thermodynamics. How about the work that you learned in physics in high school? Because I think in high school you haven't learned about thermo, about P multiplied by dV. Yes, Alvin. Yes, this is the form that I would like to write here is force multiplied by length or distance. Okay, that's the another definition of work that you have learned before. So for force, okay, multiply by distance. So basically, if you still remember this experiment that your teacher will tell you, okay, we have this block is placed on the floor, and then there is a force apply. Okay, then the block is moved. Okay, maybe move to several centimeter or several distance or meter, whatever it is. Okay, move here. Okay, by this force. So you can actually calculate the work that is applied on this block because you know the distance of the movement of the block. So we are going to use this first principle to quantify work, to derive the Bernoulli equation. Okay, so if we write that in terms of differential work, dW, it means the change of work. Differential is differential element. It means the system that is very small. Okay, very small. That's why we in engineering we like to use term differential. But if you have a problem to think about differential element, you could perhaps relate differential to sigma. Okay, if we have a system that you can analyze the difference easily, normally in calculus or in math, you will be using the term sigma to tell us about change or tell us about difference. But let's say the system is very, very small and the limit of x approaching 0, we cannot quantify that by using sigma, but we can do that by applying limit principle that you have learned by using differential term. You still can have a result on that. That's why we like to use differential. But in some way, it's actually simply just tell you about change. Okay, anytime you heard about dw, okay, differential of some properties, it just mean difference or means the change. How much is the change? Okay, so don't be too don't make yourself too because the term it looks scary, you know, but it's just a difference. How much is the change? Just simply like that. Okay, so if we apply this, so basically f multiply by dx1, we have f1 minus f2 dx2. Why? Because we have differential term here. That's why we have d here, because we want to know the change in the length of x1 and also x2. So where is this f1 and f2? I forgot to mention earlier. So f1 basically is the force that we apply at the inlet of the fluid, okay? And f2 is basically at the outlet. Okay, and then we have another definition, another important definition about force that we have learned earlier. So force basically pressure divided by surface area. That's why we can, sorry, it's the reverse. So basically, pressure is force divided by surface area. That's why if you want to know how much pressure that somebody, if someone is stand up on the floor, okay, or on the block here, you can actually measure the pressure, okay. The pressure is basically you can calculate the surface area of this block, okay. It will be this A surface area, and then you can calculate the force that apply on this person. It would normally be the weight of this person, okay, can be replaced by the weight. And you know how to calculate weight, basically is m multiplied by the gravitational acceleration. So that's why you can actually check how much is the pressure that these people has if we stand on a certain location or certain place, for example here in this block. So the same we want to apply here. If we talk about the fluid, we can use or we can relate the pressure and force relationship. So if we substitute or we move F to the left hand side, that's why our equation will be force equal to pressure multiplied by surface area. So for our case, for our pipe, the surface area will be the area of the pipe. Okay, so you should know how to calculate A1 and A2 for the piping system, okay, which you have learned many times and you have done many times actually in lots of engineering problems. Okay, so this is the force that it appears in this equation. Okay, that's why we have F multiplied by dxx is the change here, because we want to analyze differential element. That's why we will take a certain location here just to quantify differential volume. So if we have a volume that is moving this much on the right hand side, okay, or on the other side, or point number 2, the amount of volume that is moved will also be the same. Okay, volume in will be the same as volume out if we apply at the same location. That's why we can, if we know volume, we can also calculate the distance. Why? Because volume basically equal to A multiplied by X. So if we have dV, okay, we actually have A multiplied by dx. Why only X is changed? Because we don't have change in surface area. Surface area of the pipe will remain the same. Only the distance of the fluid that is traveling will be different. That's why we have dx, okay, to calculate dV. Okay, I hope that's clear for you up to here for the X term and F term. So the next step is we want to expand this equation. Okay, we want to expand the equation. Earlier, I have written that force basically equal to pressure divided by surface area. That's why we can do the same thing. We can expand the force that appears in the first and the second term on the right hand side. Okay, we replace with P1 multiplied by A1. Okay, remember P1 and A1 will be different to A2 and P2 because we have change in diameter, multiply by dx1. The same way we do for F2, P2, A2, dx2. Okay. Now we have interesting property here. We have A1 dx1, we have A2 dx2. Okay, earlier here we have this expression that I wrote here. A multiplied by dx equal to dv. Okay, so it's just simple comparison. Okay, just simple approach. You know that volume basically equal to area multiplied by the length or the distance. So we can replace A multiply by dx1 to P1 multiply by dv. Similarly, P2 equal to dv. Okay, why is only dv? Why is not V1 and V2? Okay, just imagine, maybe just imagine you have this is out of this picture. Okay, this I asked you to imagine some one pipe, not this picture. Just imagine a short pipe. Okay, just imagine a short pipe. Then you think about, let me draw a little bit. We have a very short pipe. Okay, and then this pipe initially is empty. Okay, it's empty. It doesn't have any fluid flow. And then we fill this pipe. Okay, we flow in a liquid, maybe water. Okay, and then we leave it at certain time, maybe for 1 second. We turn on the tap water for 1 second until the pipe is filled with water. But you also have the outlet, meaning that the water can leave this pipe immediately within 1 second. I just put T 1 second. So you should know that the amount of the fluid that you fill up at this inlet will be the same as the amount of the fluid. We talk about the volume here, the amount of the fluid or the volume of the fluid that leaving this pipe at point number 2 or at the outlet. So the volume, the one that entering this short pipe, okay, within 1 second, then if you leave it out, will be the same volume that is leaving this pipe. That's why no any change if we talk about the fluid. It's actually relevant to the equation number 1 that I posed in the recap. Okay, we have the relationship for volumetric flow rate divided by ratio equal to the velocity. So the volume actually is the property that is not changed here, because the amount that you put in will be the same as the amount that is leaving. Okay, hence for this derivation, we replace A1 dx1 with only dv. Even if you put V1 and V2, actually the amount will be equal. Okay, will be the same. Okay, I just write it like that. We have dv1 equal to dv2. That's why we can simplify the equation. And because we have the same dv, that's why we can somehow combine this expression. We have p1 minus p2 equal to dv. So we will leave this expression. Okay, basically we know how to quantify the change of the work for this type of system. So we've done with the first term that appear in this energy equations. Okay, any question up to here before I proceed to the second term? Any question? Okay, so I think no question, no message in the chat box. So I'll proceed with the second term. Okay, we have here dk, the change in the kinetic energy. Okay, so let us do that. The next term is the change in kinetic energy. Or decay. Okay, differential term refer to the change here. Okay, so you know that kinetic energy basically equal to mv squared divided by 2. So if we want to analyze the change of kinetic energy at two different points, let's say point 1 and point 2, so we need to take the summation of these two. Okay, so dk basically equal to the kinetic energy at point 2, okay, the final or the outlet, minus the kinetic energy at point 1, V1. So M1, this will be M2. m2 v2 square minus m1 v1 square. Again, we have an expression earlier that we can use to replace mass. Okay, we can replace mass. Okay, we remember we have density equal to mass over volume. So we can replace mass, basically rho multiply by V. Okay, because we want to connect, okay, the same term. Remember, when we take the summation later on of all the term, we need to ensure that the term somehow have the same quantity, the same properties that we can subtract. So it can give us a more simpler form that is readily available for problems that we are going to solve. So we can replace m with this expression dk. Dk, basically, okay, I can combine the two together, dv v2 square v1 square. Okay, because dv here will tell us the change of the volume. Okay, up to here, anyone understand why we have this expression? Because we replace mass with rho time density. Remember, the density will not change because we have a constant density because of the incompressible fluid. That's why we can combine the form all together. And the only form that is having different value will be the the velocity here. Okay, somehow, if you notice the expression here, we have rho, we have dv. Okay, so we later on we can actually subtract them with the other energy terms. So let us now move to the third term. Okay, the change in potential energy. So basically, change in potential energy, I can write it as du equal to m multiplied by g multiplied by h. Okay, mg h2 minus mg h1. And if we look at the picture, okay, the schematic diagram here, h1 is expressed as y1. Okay, again, it's just a notation. Okay, you can put any different notation that you like, not necessarily to be y1, while h2 is given the notation of y2. Okay, I forgot to mention earlier, anytime you would like to solve the fluid mechanics problem, you need to ensure that you place a reference or datum level. Okay, so the datum level for this case will be here. Okay, the datum level. That's why the elevation h1 and h2 is counted from the datum level or from the reference point that we are assigning here. Okay, if we replace h1 now with y1 and y2, we can do it this way, y2 mg y1. Similarly, we want to replace m by relating the mass to the density volume relationship as others. We can replace this as rho dv multiplied by y2 rho dv y1. Okay, so by combining this expression, sorry, I forgot g here. We can combine all together rho dv g y2 minus y1 to calculate or to take into account of the change of potential energy in the system that we are going to analyze. Okay, so we have obtained the three terms for the energy equations. Okay, we have dW, we have dk, and we have du. So now we want to back to the main equation again. We want to combine all the three terms together. Okay, we back to the original equation. We have dW dk plus du. Okay, so if you go back to the previous equation, you know that dW equal to P1 minus P2 dV. dk, if we go back here, equal to 0.5 rho dV V2 square minus V1 square. Okay, I'll just write it again here. Rho dV V1, V2 square V2 square minus V1 square. And then we have the potential energy term. We have above here equal to rho dV multiplied by G multiplied by the difference in the level or the elevation. Y2 minus Y1. So if you notice, there is one term that we can cancel out. Okay, we have dV on the left, we have dV on the first term on the right, and we have dV on the second term on the right. So we can cancel this term all together. So we can simplify this equation because of that. P1 minus P2 equal to 0.5 rho V2 square V1 square plus rho G Y2 minus Y1. Okay, by simple rearrangement, okay, rearrangement. If we do rearrangement, for example, you open the bracket. Okay, let's do it together. We open the bracket. We have P1 minus P2 equal to rho V2 square rho V1 square rho G Y2 rho G Y1. Okay, I hope I write all of them correctly. So now we want to rearrange them to the same the term that have the same subscript. Okay, so for example, subscript 1, we want to put it on the left, and those who are having subscript 2, we put them on the right. Okay, so we combine or we choose, for example, here for the subscript 1, we have P1. Here we have negative. Here we have also negative. We can move to the left. P1 minus rho V1 square rho G Y1, okay, will be equal to negative P2. Okay, and then we have a plus rho V2 square, and then we have plus rho G Y2. Am I right here? Right? Is this correct? Can anyone, if let me know if you spot any mistake. P1 plus here. Why I don't feel it's correct? Does anyone notice any mistake in the rearrangement? P1 plus negative P2. Anyone spot any mistake?
Shouldn't
Oh,
it be plus?
this one should be plus, right?
Yeah.
Yes, and this one should be plus. Yes, that's right.
Mm.
And then, is there anything else? Oh, this one. Yes. Is that correct now? Yes. Because the quantity should be in positive term. Yeah, I just, okay, it's should be positive when I move it around. So this is the term that we want for Bernoulli equation, all positive. So this now it looks correct. Okay, thank you for correcting me. So this is the general form of Bernoulli equation that we can apply for the fluid flow problems. If you notice, on the left hand side is the subscript 1 and the right hand side is subscript 2. So meaning that this is at point 1. Okay, this is the analysis for point 2. So if you have, okay, if you have a various location or a various point that you want to analyze, let's say maybe now you have 3. You not only having 2 location that you want to analyze, but maybe you have 3. Let me just erase all of this. Maybe now you want to put another differential element, let's say here. Okay, let's say here, you can also apply this Bernoulli equation. Okay, so maybe we have different surface area. Just imagine the surface area is different. Maybe we have a little bit. Maybe my picture will be a little bit reduction on the pipe diameter, perhaps. Okay, because if it's just the same, so no change in A basically. So just imagine we have reduction of the pipe diameter, and then we want to apply this in point 3. Let's say we call this point 3. So you can actually expand this Bernoulli equation as long as you can. Okay, so it means that, okay, here if you want to add point 3, you will be having P3 rho V3 square plus rho G Y3 square. And then if you want to analyze to point 4, okay, the list will go on and go on. So what does it mean? Okay, if we simplify this Bernoulli equation again, okay, if we rearrange this main equation, okay, the next arrangement, we can actually write this equation as P 0.5 rho v square plus rho gy actually equal to constant. Okay, equal to constant. The 3 terms, okay, first term, second, third, okay, the summation of all these 3 terms at any point of interest will be always constant. Okay, that's what we call as Bernoulli equation. So this is very useful form that really very helpful if you would like to obtain some of the important properties of the fluid flow, such as the pressure, maybe velocity, or maybe Y, or the elevation. Okay, and actually by playing around with the term, okay, let's say we have density here. Okay, we can actually play around with the term. You can replace it, relate it with mass and volume, and maybe we can change P with different relation. If you know the conversion of pressure to different properties. Anyway, the value of these 3 terms, the summation of the 3 terms will always give us a constant value. That's why we can apply them at any different location that you would like to analyze, provided that you know the properties